Instead of building a few large, isolated computers, we are now sowing microprocessors across the world like seeds. Because processing power has become cheap and physically microscopic, we can embed sensors into the physical fabric of our world, from massive factory machinery down to individual plant pots. The early internet was designed for a handful of these, heavy-duty, isolated machines sitting on desks. Today, a single office room might house 300 separate, actively chattering devices. If every one of those smart sprinklers, thermostats, and motion sensors tried to speak at once using standard internet routing rules, the local network would instantly choke on the traffic. Engineers couldn't solve this congestion by simply building smarter devices. They had to architect a 4-stage invisible infrastructure to manage the swarm. It starts at the edge, stages 1 and 2. This is the local environment where hundreds of devices must coordinate their communication without shouting over each other. The physical foundation engineered for this high-density environment is Wi-Fi 6. Older networks forced devices to take turns. Wi-Fi 6 divides a single frequency into multiple parallel lanes. Engineers compressed the gap between lanes from 312 kHz down to 78, packing 4 times as many data streams into the same bandwidth. Even with dedicated lanes, a tiny battery-powered sensor lacks the energy to run heavy web protocols, like HTTP, so these devices use MQTT. It's a telemetry protocol stripped of the constant power-draining handshakes required by normal web browsing. It allows sensors to send out tiny pulses of data only when necessary. Combined, these physical and software layers allow thousands of low-power devices to organize their local chatter without killing their batteries or crashing the local router. Eventually, that data needs to leave the building. It passes through a gateway, an aggregator that translates the local Wi-Fi web into signals built for the outside world. Sending data over long distances is a physics problem. Radio waves are absorbed by walls, water, and distance, requiring significantly more power to push through. To act as the backhaul for this traffic, telecom providers deploy macro networks like 5G and LoRaWAN, designed to cast a wide net over entire cities. Where ground-based cell towers can't reach, low Earth orbit satellites bypass terrestrial obstacles entirely, beaming data straight down to remote facilities. Networks like Starlink, spearheaded by figures like Elon Musk, are aggressively competing in this space, bypassing traditional regional telecommunications bottlenecks. This third stage provides the long-range pipeline required to aggregated local sensor data out of isolated environments and across the globe. The journey ends at stage 4, the back end. This is where the data finally arrives at centralized cloud servers. Because the data is no longer constrained by a tiny battery, the lightweight languages of the edge are swapped for heavy-duty protocols like AMQP. Borrowed from the financial sector, AMQP is built for strict transaction reliability. It ensures every packet is encrypted, analyzed, and securely stored without data loss. Millions of raw, disjointed, and fragile telemetry pulses are finally collected and transformed into a cohesive database, ready for human interaction. Why go through the immense physical and software engineering trouble to build this invisible 4-stage architecture? In a traditional factory setting, managers rely on human middlemen to gather operational data, enter it into spreadsheets, and compile reports, delaying crucial decisions by hours or even days. Modern automated manufacturing plants, like those run by Tesla, use this architecture to bring sensor data directly into the boardroom. A manager can pull up a real-time visualization of the production line, drill down to the temperature of a single motor on the factory floor, and trigger a maintenance fix before it fails. This invisible stack of frequencies and protocols turns millions of isolated telemetry pulses into a high-fidelity view of a global operation. It transforms a swarm of tiny sensors into an instant, actionable tool for management.